Today we are going to learn about building scalable stream processing architectures. We will explore how to design and implement systems that efficiently handle growing data loads, focusing on scalability, distributed computing, and modern tools. Welcome to the world of stream processing architectures. Scalability is the capability of a system to handle a growing amount of work or its potential to accommodate growth. In a stream processing context, scalability ensures that as the volume, velocity, and variety of data increase, the system continues to operate efficiently. Understanding scalability is crucial for any data-driven application, as it directly impacts the system's ability to process data in real time without compromising on performance. Today's video will guide you through the essential components, strategies, and tools needed to build scalable stream processing systems.
Scalability in stream processing refers to the system's ability to handle increased data loads effectively. This is achieved through two primary methods: horizontal scaling, which involves adding more machines to the pool, and vertical scaling, which means adding more power to existing machines. In the realm of stream processing, scalability is paramount because data is continuously generated and needs to be processed in real time. This is different from batch processing, where data is collected over a period before processing. For stream processing, latency and throughput are crucial metrics, and scalability ensures that these metrics are optimized as the system grows. Without scalability, performance bottlenecks can occur, leading to data loss or delayed processing.
A scalable architecture is composed of several key components that work in harmony. First, data ingestion is crucial. It involves collecting data from various sources and feeding it into the processing framework. This can be achieved using tools like Apache Kafka or AWS Kinesis. Next, the processing framework, such as Apache Flink or Spark Streaming, processes this data in real time. Storage solutions, such as HDFS or Amazon S3, are used to store processed data efficiently for retrieval and analysis. Networking is another critical component, as it ensures seamless communication between the various parts of the architecture. Each of these components must be designed with scalability in mind to handle increases in data volume, velocity, and variety.
Distributed computing plays a pivotal role in ensuring scalability in stream processing systems. By distributing tasks across multiple machines, distributed computing allows for parallel processing, which significantly enhances the system's ability to handle large data loads. Distributed frameworks, such as Apache Kafka and Flink, are designed to work in a distributed manner, ensuring that data is processed in real time without bottlenecks. One of the key advantages of distributed computing is fault tolerance. If one machine fails, others can take over its tasks, ensuring continuous processing. Additionally, distributed computing facilitates load balancing, distributing the data processing tasks evenly across servers, which optimizes resource utilization and maintains system performance under load. Data partitioning is a technique used to divide data into manageable parts, which can be processed in parallel. Choosing the right partitioning strategy is crucial for optimizing performance in stream processing systems. Common partitioning methods include range partitioning, hash partitioning, and key-based partitioning. Each method has its advantages and trade-offs, which must be considered based on the specific use case. For instance, in Apache Kafka, partitioning is critical for balancing the load across brokers and ensuring data locality, which minimizes data movement and enhances processing efficiency. A well-thought-out partitioning strategy can significantly impact the system's scalability by ensuring that data is evenly distributed and processed efficiently across nodes.
Building scalable stream processing systems is not without its challenges. Common issues include data bottlenecks, uneven data distribution, and high latency. Identifying bottlenecks is the first step in addressing scalability challenges. This involves monitoring system performance and identifying areas where data processing slows down. Solutions for improving data throughput include optimizing data partitioning and utilizing distributed frameworks. Managing latency involves ensuring that data is processed with minimal delay, which can be achieved through efficient resource utilization and load balancing. Resource optimization, such as scaling resources up or down based on demand, is also crucial for maintaining scalability. By addressing these challenges head-on, systems can be designed to scale efficiently and handle increasing data loads. Let's explore how Apache Kafka and Apache Flink can be scaled to handle massive data streams. Apache Kafka is known for its ability to handle high throughput and real-time data feeds. It achieves scalability through features such as partitions, brokers, and consumer groups, which allow data to be processed in parallel across multiple nodes. Apache Flink complements Kafka by providing real-time stream processing capabilities. It is designed to handle stateful computations and provides exactly once processing guarantees. By integrating Kafka and Flink, organizations can build robust and scalable data processing pipelines. A real-world example is how a financial services company used Kafka and Flink to process millions of transactions per second, ensuring real-time fraud detection and analysis. The key to scaling these technologies lies in efficient partitioning, resource management, and monitoring.
Monitoring is an essential aspect of maintaining scalable stream processing systems. Without effective monitoring, it's challenging to identify and address performance issues before they impact system operation. Tools like Prometheus, Grafana, and Elasticsearch are commonly used for monitoring. These tools provide insights into performance metrics such as throughput, latency, and resource utilization. Proactive maintenance strategies involve regularly updating systems, optimizing resource allocation, and implementing failover mechanisms. Automated scaling alerts help ensure that the system scales in response to changes in data load, maintaining optimal performance. By actively monitoring and maintaining systems, organizations can prevent downtime, ensure scalability, and deliver consistent data processing performance. The future of scalable stream processing is being shaped by several emerging trends. One such trend is the integration of AI and machine learning, which enables systems to learn from data patterns and improve processing efficiency. Edge computing is another trend, allowing data processing to occur closer to the data source, reducing latency and bandwidth usage. Serverless architectures are gaining traction, providing a cost-effective way to scale processing resources dynamically. These trends, coupled with advancements in distributed computing and data analytics, are transforming how data-driven applications are designed and deployed. As these technologies continue to evolve, stream processing architectures will become more agile, efficient, and capable of handling the ever-growing data landscape.
In conclusion, building scalable stream processing architectures is a complex but rewarding endeavor. We've explored the key components, strategies, and tools necessary to design systems that can handle increasing data loads efficiently. Scalability is not a one-time setup but a continuous process that requires ongoing monitoring and maintenance. As new technologies and trends emerge, it's crucial to stay informed and adapt your systems accordingly. By embracing these innovations, organizations can ensure that their data processing systems remain agile, efficient, and capable of meeting the demands of a data-driven world. Thank you for joining us on this journey into scalable stream processing architectures.